Okay. Okay, so it's a pleasure to have here today Yutong He. Yutong now is a PhD student in Stockholm at Nordita, but before going to Stockholm, he was a bachelor student in Pittsburgh, US, and then he moved to London and Cardiff for the master. And today he will talk about high-frequency gravitational waves. So please, and I will give you 5 minutes before the end of this.
Yeah, thank you for the introduction. Thank you for having me here. Yeah, so today I'll talk about the inverse Gertsenshtein effect as the probe of high-frequency gravitational waves, which is the title of the same. Yes, the title of the same paper, most recent work that I've done with a few people, mostly in Stockholm University and Nordita, but also Sala, who is here. This was a paper done mostly in collaboration with junior researchers, but we also had a lot of help from more senior researchers. For example, my supervisor, Axel Brandenburg, in the first person in acknowledgement here. This is a part of a larger community. It's rather informal at this stage, so I don't know if that's officially any collaboration or not, but it's part of the larger effort of the ultra high frequency gravitational wave initiative, whose goal, one of the goals is to eventually find a viable method of detecting high frequency gravitational waves. This is a white paper released a few years ago, and our work is contributing to the update of this white paper. Okay, as the name suggests, there are different elements, different parts of the story, and I divide it into 4 different parts. So first, I'll tell you a little bit of what gravitational waves are, and followed by why the high frequency regime is interesting. And then after that, I'll introduce a little bit of what the inverse Gertsenshtein effect is, and how can it be used to probe gravitational wave in high frequency regime. So first part, what are gravitational waves? Usually they are considered, they are said to be space-time ripples, with the analogy of water wave or ripple in classical physics. And they are produced by extreme events in a universe, such as when 2 black holes or neutron stars or compact objects either inspire around each other or merge into one another. A more technical answer is gravitational waves are a prediction, a result after linearizing otherwise nonlinear theory of relativity. So if you linearize the theory, and the wave equation comes out, and that's interpreted as the gravitational wave equation of motion. And they are produced by the space-time variations of a particular kind of stress energy tensor, which can be from 2 black holes merging into each other. But they don't have to be coming from astrophysical events purely. They could also be from the early universe, such as depicted by some artists online, as this picture here, where it shows turbulent motion of something. Essentially, you just need to kind of assemble the components of stress energy tensor to produce, for it to be non-zero to produce gravitational waves. So like in the early universe, when the universe was extremely turbulent and hot and with high density, all of the fields were coupled to each other. And then when they moved around, the space-time variation of that, all of that motion could have produced the gravitational waves as well. So those are examples of wave sources in addition to astrophysical ones people are more familiar with. And the advantage of studying gravitational waves is to use it as a unique probe of the universe, especially the parts where electromagnetic waves cannot really propagate through. For example, the early universe before the CMB, or of course, the late universe black hole merger sites. So these are what gravitational waves are. And why is the high frequency regime important? So I'll show you a summary of gravitational wave spectrum, the frequency spectrum, as well as some of the existing and upcoming detecting instruments listed on top, and the potential sources on the second half, the bottom half. And we have, since 2015, been detecting gravitational wave from astrophysical mergers by the famous LIGO-Virgo collaboration. So that's from since 2015, and just since last year, the last summer, there was a observed stochastic gravitational wave background in a nanohertz regime by using radio telescopes forming a pulsar timing array. So they observed the fluctuation of the timing, the arrival timing of otherwise very regular millisecond pulsars, and to infer the existence of stochastic background of gravitational wave in between us and the observed pulsars. So that's in the 100 hertz range by the LIGO-Virgo and the nanohertz low frequency by pulsar timing arrays. And laser interferometer space antenna, LISA, is going to, the plan is for it to be launched in 2035, and its aim is to detect gravitational wave in the millihertz range to kind of bridge the gap between 100 hertz and the nanohertz. So these are all very exciting. So there are many dedicated detectors below the kilohertz regime, going up all the way up to roughly 1 kilohertz, capable by LIGO-Virgo interferometers. And on the contrary, there are not a single dedicated detector above kilohertz range at all. And by itself, that shouldn't be a problem. If there's nothing interesting in high frequency regime at all, then why bother building a detector? But there actually is a lot of interesting stuff to be discovered potentially in high frequency regime, very broadly defined to be just way above kilohertz. So the high frequency regime is important because the first thing is there is no existing mechanism in known physics described by, let's say, the standard model of particle physics that can produce gravitational wave above kilohertz. Anyways, I mean, that's one of the motivations to not building any dedicated detectors above that range. However, we know that standard model is not complete due to a lot of different shortcomings. And there is a whole array of neophysical mechanisms that can be responsible for producing really high frequency waves, essentially from the kilohertz up to the cutoff scale, if you want the cutoff scale to be the Planck scale. For example, a lot of beyond standard model particle theories complementing the known physics in the early universe could have produced really high frequency waves, primordial black holes if they existed, and if their masses were way below the one solar mass, or phase transitions similar to the QCD phase transition and the standard electroweak Higgs phase transition also in the early universe, but high scale meaning really high temperature. So that has to do with whatever beyond standard model mechanism you assume. They kind of go hand in hand. But these are all examples of sources of high frequency gravitational waves. So essentially any detection of high frequency gravitational wave would automatically point you to the existence of beyond standard model theory or neophysics. And any non-detection of high frequency gravitational wave, if you infer some sort of upper limits instead of a direct detection, that would give you information to constrain the parameter space of neophysics. So in general, high frequency regime of gravitational waves is really important and interesting for us. All right, and then the third part is the Gertsenshtein effect, or its inverse. So the Gertsenshtein effect describes the conversion between gravitational and electromagnetic waves. It is an entirely classical phenomenon, and the conversion happens at the same frequency. So a terahertz wave would convert from one side to another, still keeping at the frequency of terahertz, for example. And it's classical, but with quantum corrections. But to the leading order, you can treat it as a classical event. And this is a picture of, a description of how it happens. So you need an external magnetic field somewhere indicated by this B here, pointing up in this case. And then you have gravitational wave indicated by its strain amplitude, h mu nu, that travels from left to right. So perpendicular to the direction of the B field. And at the other side of the B field, you have a fraction of the h mu nu, the gravitational wave strain amplitude, converting to photons. And this conversion carries a small probability it's not zero, but it's very small. And the conversion probability depends on what you assume the magnetic field to be, its strength, its correlation length. It does not really depend on the incoming gravitational wave property, as long as you have a non-zero gravitational wave strain coming into the field. So this picture describes the inverse. The Gertsenshtein effect without the inverse would be the other way around. You can shoot photons into the field, and there's a probability of converting into gravitational wave from the other end. So this is what the effect describes. And then the last part, the technical part, is to kind of combine all of these together and use inverse Gertsenshtein effect to hopefully detect high frequency gravitational wave in the future. But in this work, we weren't able to. We placed upper limits. So the recipe of deriving these upper limits on high frequency gravitational waves is to assume a stochastic background of high frequency waves from the early universe due to we're remaining model agnostic, but there is a large range of possible sources in the early universe, like I mentioned before. So we assume the presence of the high frequency waves as a whole background. And we also assume the presence of magnetic fields between C and B and today, and also some properties associated with these large-scale magnetic fields in which the gravitons can convert into photons. So we have a B field from C and B to today, and then as the primordial high-frequency gravitational wave propagate through the C and B from the C and B until today, they convert into electromagnetic waves. And then because this would essentially be photons produced after CMB was released, they would manifest as excess photons, distorting the blackbody CMB spectrum. And there has been a few these radio excess measurements observed at the current day, and we interpreted those radio excess as due to the incoming high frequency gravitons, gravitational waves. So that was one step, and then we also considered we did a simple forecast study and see whether improvement can be brought by future instruments such as SKA, and which is a solid upcoming telescope, and also more conceptualized instruments at the proposal or conceptualization stage, some of the future CMB precision surveys as well. So we also forecast the improvement that can be brought by those instruments. And this is the result following the recipe shown in the previous slide. This is the kind of the first step work. So to the first order, we assumed a really simple, reduced the 10⁻⁻ centimeter signal model. And we also assumed that the reported radio access at the current day is entirely consisted of a high frequency gravitational wave, whereas in reality, of course, that radio budget can consist of a lot of other different sources. We also assume the perfect foreground removal associated with the reduced 10⁻⁻ centimeter signal models. And then, so the result can be summarized on this picture, where horizontal is the frequency and the vertical is the gravitational wave energy density. So that's non-dimensionalized, and it's normalized against the critical energy today. So the two horizontal lines, respectively indicate the overclosure limit of the universe. So it's the first black line up here indicates the critical energy density of the universe today, and then the dashed line here indicates what's the so-called N effective, or the BBN, Big Bang Nucleosynthesis limit, which is the kind of theoretically inferred upper limit of how strong non-photon components of the radiation can be at the present day. And gravitational waves are a form of radiation. So in principle, gravitational wave, at least a stochastic background of gravitational waves from the early universe before the time of BN, should be at most below this BBN limit at 10⁻⁻⁶, roughly. So those are the two references to kind of guide your eyes. And then we have the vertical color bars indicating different instruments reporting the existing radio access over CMB. Those are edges, LOFAR, MWA, RK2, ACT, across ranges from like 100 megahertz to 100 gigahertz-ish. They are way up. They give you upper limits of gravitation wave around the order of 10 to the 10 above, 10 to the 12 maybe. So that's really unrealistic. I mean, because critical energy of the universe is here. So the existing measurements are not enough under our simplified assumptions, and we did a forecast on the SKA's capability to improve this upper limit, and as well as some proposed CMB measurements on a different frequency scale. So these are indicated by the shaded areas in the respective frequency range, and all of these are much better. Much better results, and the existing constraint can be much tightly improved due to this upcoming measurements of the sky following the same procedure. So these still follow essentially the same simplified assumptions. So you can imagine they can be tightened even further. For example, by joint analysis with other components also contributing to the radio access, such as axions if they exist, neutrinos, they surely exist, and some other possible mechanisms such that if gravitons don't saturate all of the radio access, then the component responsible by these gravitons could be tightened and pushed down even further. So the goal is kind of to see how much further you can push it down for future directions, and whether it is possible to have some of the future instruments, for example, SKA, to reach at least below the overclosure limit and possibly the BBN limit. That's one possibility. And of course, we made quite simple assumptions about the magnetic fields, which can be made more realistic by using magnetic fields from numerical simulations, which Salome is an expert of. Those are, for example, the two possible ways to go forward. And that's it. I kind of wanted to leave it maybe a little bit shorter than 25 minutes to see if you guys have any questions.
Thank you very much. Question to the speaker? Please.
So actually on this graph,
yeah.
Super cool talk, by the way.
Yeah.
Very interesting and exciting. And Salome's talked a bit about inverse Gertsenshtein effects in group meetings before, so it's really cool to learn more about it. With this figure, how does SKA mid compare? Because you would think I work in the image domain mostly, so maybe this kind of space is a bit different, but SKA mid should be a lot more sensitive than SKA low. So have you looked at all about how mid would be able to compare, or is it just kind of the wrong frequency range for this effect?
We didn't look into mid, but it's a good point. We also mentioned the mid as one of the future possibilities in our work, because it would kind of bridge the gap between the pink part and the blue parts. So that would be good. I mean, this effect is universal. It doesn't care about which frequency range it is. So mid is definitely something, if we have time, we would want to include.
Yeah, in that frequency range with the good resolution, might do better in terms of foreground removal. Yeah.
Well, but if you're considering it like in terms of foreground removal, we already assumed the very idealistic, perfect.
Of course, yeah.
Removal.
Yeah. Questions? I have one. So what do you mean with the reduced 21 centimeter modeling? So it's just a simplification of, so which kind of simplification?
Normally there's 5, 7 or even more parameters that go into the n-body code to simulate dark matter and those dark matter particles and their interaction, and how the 21 centimeters come about in the universe during reionization. We did not, so we added one more parameter that indicates how much additional radio signals can be due to the gravitons. So a full modeling, a full sampling of that model would require all of the 21 centimeter parameters plus that one from gravitons. But we didn't include all of the 21 centimeter model parameters.
Okay, but it's because of like it's a time demanding process, because as far as I know, there are tools that are pretty fast in like simulating possible signals. So like why, like, is there an improvement that you plan to implement in your estimates, let's say? Or?
In the future, definitely. The first time I used statistical sampling for like statistical inferences, so I wasn't. I guess I wasn't ready to do a full sampling, so I just picked the two parameters that were kind of considered as essential for 21 centimeter signals, and did not include the rest. The future step is definitely to include all of them, plus this one additional parameter.
Okay.
Yeah.
Other, please?
Yeah.
So as far as I understand, this process you are studying is something which is predicted theoretically. You say that it's a classical process, so I guess you mean that it's a prediction of general relativity. I mean, you can convert these gravitational waves into photons in the presence of an external magnet. But again, as far as I understand, this is something which has not been proven from the experimental point of view.
No.
So the point is, what would be, I mean, here you are discussing the possible use of this effect to know something about the gravitational waves in the high frequency regime, but what would be an actual experimental proof that this process, this theoretical process is at work? I mean, empirically.
Good question. The effect is it's a two-way effect. You can produce gravitational waves from careful manipulation of photons and laser beams, and there have been field proposals, even a few patents of gravitational generation in manually controlled lab, because then the magnetic field, the information is entirely known and everything, and you can kind of try to produce gravitational wave in that sense. And if you were able to do that, and then correspondingly detect gravitational wave produced in the lab, that would be the proof of not inverse but Gertsenshtein effect. And if that is done, then the inverse is, well, I would be happy to take that as.
Probably the problem there is to be able to measure such gravitational gravitational waves in your lab. With
gravitational wave for gravity, everything is very tricky because gravity is super weak. Everything about it is kind of it requires extremely precise measurements. But there has been, like, in this ultra high frequency gravitational initiative, some other people are actually looking into producing gravitational wave in the lab, or inverse Gertsenshtein effect in the lab setting, where you try to detect this high frequency wave in the astrophysical magnetic field setting, but also in the laboratory setting. I don't know what the concrete experimental proof, like what form it would take, but probably somewhere along the direction of lab controlled environment.
Any other question? If not, let's thank the speaker again.